Let's begin. All right, we are in the heat of it. Okay, things are getting harder. I can see from your homework assignments. Okay, the project. So things are getting real. That's the reality of it, and we're barely scratching the surface. So again, this is advanced material. It will require a lot of commitment on your end, on your side of things, right? So you have to put the time and effort to get up to speed on things that maybe you have a gap in, and on new things that we're learning, right? There's thousands of discussions and topics that need to be discussed still, a lot of issues to talk about, and we are barely scratching the surface. But I hope that by the end of it, you've seen enough to be able to try to make sense of something that you will learn next or later with a different method or with more advanced methods. If you think about it, we're doing stuff that they did in the 60s. Like, this is 60s technology. You would stone me if I brought you a phone, from 1990, like those old Motorola's, right? So yet, and you'd find that archaic. So this stuff is old stuff, right? Just presented in a new perspective, and it's frankly easier now. We have Python and slicing. Can you imagine doing this with Fortran arrays and having to kind of index our way through weird indexing with Fortran and bad, just no visualization? So, think about the positive things. Despite how hard it might appear, we have a lot of, it's much less harder than it used to be, frankly, okay? So without further ado, last time we covered the finite volume method, and the finite volume method, I said, has nothing to do with Navier-Stokes equations with fluid mechanics. It has roots inspired from fluid mechanics and transport theory, where we take a control volume, we do conservation on it, etc. Absolutely. And we applied it to a diffusion equation the other day, right? And an advection equation. So the finite volume method is just a numerical technique, like the finite difference, like the finite element method. It treats things differently. It assumes a small control volume and solves the equation in their integral form or the weak form, and integrates those, makes approximations, etc. We covered that. So it's just a standard numerical method. But when applied to Navier-Stokes, we think it has good advantages and also naturally leads to the staggered grid, which I talked about at the end of the finite difference project that we did together in class, where we demonstrated lack of mass conservation properties in the finite difference scheme because div grad is not consistent with the Laplacian. And then we alluded to that by saying, we can fix this if we put the velocities on the faces of the control volumes, then apply div grad, so put velocities and pressures at different locations, you apply div grad, then that becomes consistent with the Laplacian, and everything works well. All right? So the finite volume method, when applied to Navier-Stokes, will also give us one more indication that the staggered grid is a natural arrangement for fluid mechanics. Okay? So we're going to start with the weak form of the equations, which is the integral form applied on these differential equations that we saw earlier. And we have converted all volume integrals to surface integrals. So we already applied Gauss's divergence theorem. So look, for example, at the continuity equation. So these are the equations for constant density incompressible in 2 dimensions. We know we're dealing with those equations all along. So starting with the continuity equation, the differential statement that says that div u equal to 0, if you integrate that over a volume, okay, then, and you turn it into a surface integral, it becomes the surface integral of the fluxes, or the mass flux through all the surfaces, needs to add up to 0. So whatever, this is a statement, and it's more intuitive if you think about it. So if you look at the integral, you're summing the velocities at each of the surfaces surrounding the control volume. And you're saying all of those velocities, they must add up to 0. The net fluxes coming through the surface must add up to 0. That makes sense. Whatever you're bringing in, because you cannot compress it, it must leave. Okay, so it's a very natural statement to look at it this way in the integral form. Then you have the x momentum and y momentum equations. Again, density is constant, so I'm dividing by density. You have the volume integral for the time derivative terms. Those are the terms on the left. Then surface integrals for all the fluxes, the convective fluxes, the diffusive fluxes, but also the pressure. So the pressure is not a flux, it's a surface force. Okay, the pressure is not a quantity that enters, it's a force, right? But it still results in a surface integral, which indicates that its action is on the surface of the control volume. Okay, so those pressure gradients that we had dP by dx and dP by dy, they just simply turn into the surface integral of the pressure itself, okay, along the unit normal, so only the normal component, right, for the pressure. Well, it only acts normally, right? So the pressure times the area, that gives you that force, right, over that surface. So that's what this integral is doing, right? So P with the area gives you that force on the different surfaces of the control volume. And you can reason your way through these convective fluxes. This is the convection of u momentum with the velocity field vector u. Convection of v momentum with the velocity vector field u. Okay, so this has two components as well, right? U and v, and u and x and y components, x and y components, and same here. Okay, these are quantities that go in two directions, right? In 3D, you'll have three dimensions. Okay, and again, the n is a unit normal, always pointing away from the surface. Okay, so that will help you distinguish which component is going to contribute to the control volume. It has to be coming into the control volume. Any tangential fluxes will have no contribution. They don't bring any mass or any momentum into the control volume. Okay, so this is the transport of momentum by convection, transport of momentum by diffusion. Okay. All right, so let's start by applying the finite volume method on all of these, on each and every one of those equations, each and every term. We're going to go term by term. Okay? We will start with mass conservation, and forget the diagram for a second. Just consider a control volume. Forget these velocities for a moment. They should have been animated, but they're not. So assume they're not here. Just think of the gray square with that blue dot in the middle. Okay, that's where we said our quantity is going to live for the finite volume method. We're going to place the average quantity at the centroid of the control volume. Okay, so that's where generally our unknown is going to live. And then if you take that mass conservation integral, surface integral of u dot n ds, and integrate that over this control volume, an exact statement says, again, if you review last lecture for the finite volume method, because this control volume has four faces, we're going to add up this integral over each one of those faces. Okay, so that's the summation over the faces of the control volume of this integral u dot n ds. Now, u is u and v, right? So dotted with n, the outward unit normal, is going to give you the x component, y component, x component, y component, okay? Now, when you do this, and you make the assumption that along this entire surface, we're going to take one integration point, which is at the center, so that's like the midpoint rule, or like the average over that volume. So u, the velocity u, is not changing over that surface. We assume it's just constant, and it's located over here. You get this equation. Okay, so the integral of u dot n gives you u east times delta y, right, because you have that ds, okay, plus, minus u west times delta y, right, because u and v are aligned, we assume they're aligned in the positive direction. Unit normal is negative, you get minus u west. Now, if u west is negative, then it will adjust the sign accordingly, okay? So don't worry, these are signed quantities, u east, u west, etc. But the assumption is we draw our velocity vector in the assumed positive directions. We dot them with the unit normals, so they give us the appropriate flux direction. And then if the sign changes, it will take care of itself. Same thing for these surfaces. U dot unit normal for this north face is going to give you Vn, so V north on the north face. Remember, I used the nomenclature lowercase east, west, north, and south for values of the fluxes along the faces, and capital east, west, north, south for the cell centers. Okay? So you get V north times delta x, which is this area, right? And V south dot delta x. If you should be able to see this on the fly, right? U dot n ds, if U dot n is constant, you take it out. ds is simply that segment times unit depth, okay? So then you divide by, because this is equal to 0, you divide by delta x, delta y, and you get, what looks like du by dx plus dv by dy, right? A discrete formulation of du by dx plus dv by dy. But I want to note one thing before I continue the discussion. Note that I put n plus 1 here on purpose, because if you remember our projection algorithm, we need to make sure that our new velocity is divergence-free. The velocity that we move in time is divergence-free, though the velocity at n plus 1 is divergence-free. So I specifically put n plus 1 here to remind you of that condition. Okay? Now this gives us U east, U west, V north, and V south, which are velocities. As far as we are concerned, these are unknown velocities, right? We're solving for them. We're trying to develop the discrete equations to solve for these quantities. Okay? And okay, so now you ask yourself, well, what the heck is U east, and what is U west, what is V north, what is V south? Well, now this gives us an opportunity to talk about the placement of variables. If we were to place our momentum quantities, U and V, at the cell centers, so you would have U and V living here, U and V living here, then you would need to do an approximation for this one. Maybe take the average, like we did in the previous lecture, right, for the flux at the face, etc. Or you could say, well, at a control volume, the continuity equation, which sets the Navier-Stokes equations apart from all other advection diffusion equations, right? Advection diffusion have no conservation properties like the Navier-Stokes. They don't have an algebraic constraint on them, right? They're conserved in the sense that, yeah, whatever is coming in is leaving. With momentum equations, you need to satisfy that algebraic constraint, div u equals 0. So in essence, this equation is very important. It tells us something that at a control volume, naturally from this finite volume approximation, the velocities there are velocities that naturally live at the faces of the control volume. Because we have freedom in the finite volume method to place things wherever we want. Remember, the face, the location on the face is a degree of freedom. We can place variables over there if we choose to. So why not put the velocities at the faces of the control volume? So we'll keep the pressure at the cell center, okay, keep it over here. But we're gonna, what if we place the velocities at the faces of the control volume? Could we do that? Absolutely, we can do that. Now that is the same idea of the staggered grid. The advantage of this, if you remember that lecture with the finite difference method, is that it will make div grad consistent with the Laplacian, and it will resolve our mass conservation issues immediately. If we were to place the velocities at the cell centers, you'll get a finite volume method, but that's still not divergence-free. And you can do that. There are methods, they call that collocated grid arrangement, if you've heard of that. So Fluent, for example, does a collocated grid arrangement. All of those collocated, where they place the velocities and pressures at the cell center with finite volume, they are not discretely divergence-free in the cell centroids. They're divergence-free at the faces, actually, which is not the quantity we want. We want to be divergence-free inside the control volume, because our control volume is our control volume. We want everything that's going into the control volume to leave it. Okay? So I have a statement here that says, well, we have the freedom to place the velocities, and this, in addition to the other discussion about div grad, lends itself to defining what we call the staggered grid. Okay, so this staggering is the essence of getting true discrete divergence-free conditions. Okay, so there are several ways to stagger variables. Okay, Now, staggering in general just says we're going to place the different variables at different locations. In this case specifically, we're going to put U, P, U, P. It's like, you know, we stagger things. But you could stagger to the left. You could stagger to the right. You could stagger to the top. You could stagger in all sorts of weird ways. But as long as the velocities are placed at the faces of the control volume, then the meaning of staggering to the left or staggering to the right only means how you index quantities, the indexing that you are going to assign to these quantities, which will be very important when we are writing code. Okay? So in this class, we will stagger quantities, we'll stagger momentum, velocities to the negative faces of the control volume. What this means is that the indexing of the velocities on the minus sides of the control volume, so the plus side are the plus, this is the plus x face, this is the plus y face, so they're aligned with the positive normal, and this we call the minus x side, minus y side. If you haven't heard of this nomenclature before, you hear it now. Okay? So this only means that the indexing of the velocities is the same on the minus side as it is for the cell centroid. So if this is Pij, if this is the ij control volume, then this velocity will be ij, and this velocity will be ij. Okay? This will become clearer as we build that full staggered grid in the end. Okay, so this will be very important, because when we create our arrays in the end, and you say, okay, you're trying to access P54 in cell 54, then U54 and V54 are going to be located here. Okay, they're going to be on the left side of that control volume. So it's only a convention. If we had staggered to the right, then this would be Uij, and this would be, to the plus side, this would be Vij. It's fine. It's just a convention that we use. You know, in this class, we're going to adopt staggering to the left. It's a common way of doing it. Some people stagger to the right. Doesn't matter. Okay? It's just a matter of indexing. That's the only thing it will change, just how you index things. But know for now immediately that because we're staggering to the left, if I'm at cell Pij, then this velocity is automatically referred to as Uij, this one as Vij. And then the one next to it, so you'll see I draw this diagram always, this kind of L or whatever you want to call it, okay? That is how we are staggering in this class. You will see that you cannot survive without drawing a grid every time. In fact, so Maher, for those on YouTube, Maher is one of my PhD students now. He actually prints, we always print out the staggered grid that I'm going to share with you eventually so that we can reason our math around it. So I will give you a diagram of this full staggered grid that you have to keep printing to look at it as to make sense of doing the implementation, because it's extremely complicated. And guess what? It's doing only the simplest thing that people do, which is just counting. You're going to be counting, oh, what is the index of this cell? How far is this cell away from that cell? It's just counting. Okay, but you still need that grid to be able to reason about it. Because once we lay out a full grid with Uij, Vij, all sorts of variables, it's going to get really confusing. Okay? So we stagger to the left. What that automatically means is that this velocity over here is Ui plus 1, j, and that velocity is Vi, j plus 1, right? Automatically. Okay? The cell next to this is Pi plus 1, j. Okay, so this would be Ui plus 1 because it's staggered to Pi plus 1. And the velocity next to it would be Ui plus 2, and so on. Okay? So that's great. So now we have our staggered grid. Now, staggering also implies two other important things. And because you're placing the velocities at different locations on the grid, now to do conservation on the momentum, you need to apply conservation on a control volume, because this is a controlled finite volume method. You can't just do conservation on the x momentum. Like, where's the control volume for the x momentum? Where's the control volume? That's not it anymore. This is the control volume for mass conservation. Really, this is the control volume for P, okay? Because P and mass conservation are tightly tied in together, right? But we haven't defined a control volume for x momentum and y momentum. We need to, otherwise, where are we going to integrate the u momentum and v momentum equations, right? We have surface integrals. We need to integrate them on u control volumes and v control volumes. So what do? We draw, we call this gray control volume the scalar control volume. And then velocities and momentum have their own control volumes. We're going to draw a control volume for the x momentum, shown in yellow here. And guess what? It's going to be centered on the x momentum velocity, right? So I'm going to center it on u. So this yellow control volume, it shares a face with P, but it's centered on u. And same thing, we're going to draw a control volume for the v velocity component, or the y momentum component. And it's going to be staggered to the left side, or to the negative side, okay? When we go next and integrate the x momentum equation, all those surface integrals, they're going to be applied on the yellow control volume. When we integrate the y momentum equation, they're going to be applied, the surface integrals, going to apply to this green control volume. We do all of this for the sake of mass conservation. It is so important to conserve mass that we're willing to spend the time and effort to do this, to figure this out, okay? So now you can imagine all the kinds of quantities that you're going to be dealing with, okay? All right, let's build that together. So this is our control volume. And then finally, our continuity equation then reads at point ij, at some arbitrary control volume ij, we had u east minus u west plus v north minus v south. It's really ui plus 1 minus ui plus vj plus 1 minus vj, okay, over delta y equal to 0. So that would be our continuity equation. We will convert that into a pressure equation later, but I needed to figure out the indexing now, okay? I need to figure out the indexing. Okay. Let's start with x momentum. The time derivative for x and y momentum, those require, we're going to do forward Euler on those, so there's no need to talk about the time derivative really, because it's just un plus 1 minus un over delta t times delta v, so it doesn't, excuse me, that doesn't matter. So the first complex term is the x momentum convective flux, okay? And this is given by the surface integral on the x momentum control volume. So that's that yellow control volume, okay? We're convecting the x momentum of the x momentum component, u, okay, per unit mass. So rho u per rho is u, right? So that's u, the u velocity convected with u and v. So it convects itself and convects itself with the v component. But this needs to be carried out on a u control volume, okay? So the nomenclature that we will use, I will call this the u control volume or v control volume, call those. Or we will call them the x control volume or the y control volume, okay? We will use nomenclature the faces of the u control volume, the x face, y face, x plus, x minus, etc. So all of that nomenclature is interchangeable, okay? And for cell-centered, we'll call them cell-centered. Those are the gray control volumes. Okay, so now for reference, I'll take my time with this first one, and then we'll go faster with the other ones. Okay, so for reference, I'm going to take two cells now, two control volumes, Pij, Pi minus 1j, makes sense. Okay, and then Uij lives here, correct? Ui plus 1 lives there, and Ui minus 1 lives over there. And we're staggering to the left. You have to do this every time. Seriously, to this day, like this morning, I was working on one of the codes we're going to do in class. I had to print this on a like in A3 size, because I don't see anymore, just to be able to see my grid layout. So you have to do this every time to understand your indexing. It's only counting, but it's really annoying, okay? All right, so naturally then, this would be, you know, if this is Vij, this would be Vij plus 1. And same for the other ones, right? This would be Vi minus 1j, right? Because notice these L's they share the same index as the cell center. So once you know the cell center, you do the staggered ones, and then you deduce the other ones, the rest, okay? So this one is at VI minus 1 and J plus 1. This is important. This indexing is going to be very important. It's going to be identical to what we write in the code. So if we get this right on the board, these slides, they will guide us when we do our implementation. Okay. We're not done yet. Now we draw the U control volume. Now, the convective flux is going to bring U velocity, the U component of momentum, or the U velocity, through all of these faces using U velocity and V velocities. So let's see how that works. So now I'm going to move this up here. Okay, so we agree with the indexing. Now, this is going to be our reference. We will use it to think about how we're gonna draw these. All right, so I'm gonna take this control volume out. So now forget that this is part of all of this. I have a U control volume. I should be able to integrate this X momentum convective flux. I want to be able to integrate it over this control volume. So let's see what this gives us. So if you carry out the integral over all of those faces, so you have on the east side, you will have U times U dot N, which is another U. So you get UU east times delta Y. So that's ds, right? And then on the west surface, so this would be this surface, you have the U component, and U dot N is minus U. So you get minus UU at the west location, also times delta Y, right? And then the one on the north, you have the U component, and U dot N, that's going to give you V, right? Because U is UV, N, which is pointing upward. So you get only the V component. So you get VU at the north face times delta X, which is the area. And then finally, the bottom face, you still have, you're advecting U, but then U dot N for the bottom face or the south face is minus V, right? Because that's the V velocity dotted with minus, with 0, minus 1. So you get minus V at the south location times delta X, which is the area. Okay? So that's just the integral. Okay. So now if you go and place those over there, this is what the fluxes look like for the U momentum control volume. So now the control volume has faces, and those are shared with the cell centroids for the pressure. But you know, we don't have to put that other control volume over here. But these quantities live at that point. So when I draw that arrow in the center of that face, it's because we made the assumption that that integral has the average value lives at the center of that face. Okay, that's a very strict and thorough argument. I cannot put UU lives here in the centroid of this face, not here, not here. It lives on the centroid. Okay, so if you're doing order analysis for the fluxes, your spacings need to be based on the centroid. Okay, so UU east and UU west, VU north and VU south. Okay, so those are the fluxes that constitute this one. Okay, those are the fluxes that constitute all of this. Now the arrows, I just drew them with assuming everything is going in the positive direction, but they could be in all directions. They could all be coming in and coming out from here. Doesn't matter. The code will take care of it. The solution process will take care of it. Okay. These animations took me a very long time to just kind of make them work. So, okay, great. So now we placed it back on a U control volume grid. Okay. So I removed the pressure control volumes. Okay, so now we have UU east, which is U east times U east. UU west is U west times U west. VU north is V north, U north. And VU south is V south, U south. Now, these are north and south with respect to the U control volume, not the cell center control volume. These are with respect to the yellow control volume. Okay? Now, those quantities, we don't have any variables living over there. The only variables we have, they live at those squares. The yellow squares for the U and the green squares for V. So we don't have variables that live here. We have to approximate these quantities. Remember, we are solving for these guys, the yellow and the green ones. these fluxes here have to be constructed using approximations with variables that we are solving for. Okay? So, easy. What about U east? What do you think we can do for U east? U east. So it will be ui plus 1 plus ui over 2, right? Second order approximation. Looks good. What about west? Correct. Yep. So it's the average between ui minus 1 and ui. What about u north? Oh, I should have given you north. What about u north? That one is fun. No. U north is here. U. So that's the u component. So where do you have u velocities? You do. You have a u velocity above it, right? But we're trying to express it in terms of those. You don't know these either, right? So what is u north? Yes. Yeah. So you have to grab uij and uij plus 1, the one above it, right? Until you hit the boundary, right? You hit the boundary, you'll have a specification, but in the middle of the control volume, you have variables placed at those u control volumes. So we have to bring in the one above it. So now we have uij plus uij plus 1, the one above it, okay, over 2. What about u south? Remember, I need v south and u south and v north. We're doing the u's first. What about u south? Same thing, the average between this guy and the one below it, okay? Yes, we don't know what they are, but we're making expressions in terms of those unknowns to solve for them, right? Yeah. Okay, so now what about, we're still missing, so we have u east, u west, u west. We have u north and u south. We still need v north and v south. What is v north? From using existing variable locations. What is v north? So v north lives here, right? Where do we have the closest velocities? V velocities. Yeah, average of the ones at the corners, right? So now, programmatically, the code doesn't know that these live here or live there. We, as humans, say that they live here and they live there. Programmatically, you're just going to say, oh, this is vij plus 1 plus vi minus 1 j plus 1 over 2. That's it. That's all you will have to say. Okay, because you are looping over points ij in the u momentum space. Make sense? Okay. So, and remember, this is all relative to this uij, which is relative to pij, which lives here. Okay? So just keep that in mind. It gets really complicated. But if you do it once like this on the board, you're honest. You don't have to do it. You can take this blindly and implement it and be just fine. So indeed, v north is the average of those two velocities on the north, on the upper corners, upper left and upper right. And what about the last one, v south? Here, v south is going to be the average of these two. Okay, these are second order approximations. Perfect. Whew. So now compare that to the finite difference method. They are quite different. Okay, there's no comparison anymore. Okay, just the staggering alone just changed everything. But it made things more compact, right? Closer to each other. We're always close to those control volumes. Okay. So now let's do the y momentum. Really, the momentum, the convective flux is the hardest one. So that's why I started with it. So now let's do the y momentum convective flux. We could probably do it faster. So the y momentum convective flux is the surface integral of this y momentum per unit mass, v, times u dot n. It's advected by the entire velocity field. Now, this surface integral needs to be carried out over what control volume? A cell-centered control volume, a v control volume, right? Because that belongs to the equation for the v momentum. Yeah, and it will live. So let me even say this. The result of this integral, where does it live? It lives at the cell centroid of the corresponding control volume. The net flux, you integrate that flux, that value actually lives at the centroid of the volume it represents. So the result of the y momentum convective flux will live at the centroid of the y momentum control volumes. Okay? It has to live there because it's the net integral over that volume. All right? Okay, so let's do the same. We get Pij and Pij minus 1. So now I have to do in the y direction because we're doing y momentum. And again, Uij, Vij, they live here. You get Uij minus 1 and Vij minus 1. The indexing becomes kind of just natural. And I will need Ui plus 1, J minus 1. I need these guys and that guy as well. Okay? All right, so let's draw a Y control volume now, a V control volume. All right? So you get this guy. And then I didn't animate it, but it would translate. So all I did was take this guy and move it over here. Now, I put these corner velocities because you can easily forget their indexing. But for Vij, the indexing, this is Vij plus 1, Vij minus 1 below it, Vi plus 1j next to it, Vi minus 1, because we are ordered. But with this one, there's like, it's not very obvious kind of how to think about it, right? It's not very obvious how to place these corner velocities. So that's why I do this first. I put those velocities here, and then I take this and put it here, leave the corner velocities to help us think about it correctly. Okay. So same thing happens. The integral of Vu dot n ds would be equal to all the convective fluxes of the V momentum component. So there's a V in every one of those terms, convected with U and V as well. So you get UV in the east direction times delta Y, minus UV in the west direction times delta Y, plus VV in the north face times delta X, plus VV on the south, minus VV in the south face times delta X. Okay? So now we need U east, V east, V north, V south, and U west, V west. 6 terms. All right? All right, let's get started. U east. Let's do U east. Which one? Yeah, these guys, right? The average of these two is U east. Agreed? Okay. That gives us U east. What about U west? Of the other corner. That's right. So you get the average of those guys, Uij and Uij minus 1 on the other corner. It's easier to just point to them, right? Okay. Now what about V east? So V east lives here. Now I do know that there's another Y control volume next to it because this is a structured grid. Okay? So V east lives here. Yeah, so V east, I'm doing this one. Because we got U east, U west, I'm going to do this one now. V east is between these two guys. Vij and Vi plus 1j, right? So Vij, Vi plus 1j. Now V west is Vij, Vi minus 1j, the one to the left, right? Left, right? Left, correct, okay. Now what about V north? The one above it, right? It's the Vij and Vij plus 1. It's good to, we will use exactly these indices when we write the code. We're going to use those indices. That's why I'm doing this exercise now. It's good to do it theoretically on paper, and then once we do, we're going to do with for loops. Slicing is harder. We'll do it after, but we need to do the for loop first because there's a lot of indexing going on. And finally, the V south is this control volume, this value, plus the average below it. Okay, Vij and Vij minus 1. Now, where does this convective flux live? The result, we know it lives at the cell center because it's going to contribute to the evolution of Vij here in the cell center. Same thing for the pressure gradient, same thing for The diffusive flux, they will all live in that quantity. Now, the reason I say live over there is when you go and start asking for order of accuracy, you have to know the location of your variables to know how to measure your spacing, etc. Okay? It doesn't live 1/3 of the way here or here. It lives in the middle. Okay? Delta y over 2 and delta x over 2. Okay? So those quantities, they live in the middle. They are only second order if they are in the middle. If they're not, if you place them somewhere else, they will not be second order. Okay? All right. So now let's go back to the x momentum, and let's do the x direction pressure gradient. So that's dp by dx, or the integral of p n x ds. So only on the okay. So integrated over, that will be integrated over a u control volume. So again, that's our u control volume. And if you take that equation, it's kind of obvious. It's kind of very easy, right? Because the pressure lives already on the x basis of u control volume. So the integral of p n x ds, so that's only, we're doing only in the x direction, right? Is 1 over rho this integral p ds. You get p east times delta y, which is the area, minus p west times delta y. And p east is pij, p west is pi minus 1j times delta y. So that gives you that pressure gradient across the x momentum control volume. Okay? Same thing for the y momentum. Integrated y momentum pressure gradient, so that's going to be dp by dy, or the integral over the surface and only the y components of that surface. Okay, so you get this. And indeed, if you remember our staggering, you start always with pij, you get uij, vij. The one below it is pi minus 1. Because I'm integrating over pij over vij, I need the one below it, so that would be pij minus 1, be this guy. And I have pressures over here, so I can evaluate my dp by dx, dp by dy, so that it lives in the cell center, really. Or you do it in integral form, which is kind of more rigorous. You get p north minus p south, okay? So p north delta x minus p south times delta x. And that would be pij minus pij minus 1 times delta x. This indexing is very important. We're going to use this indexing once we write our code. So I'm going to go back to the slides and go over, okay, this is it, this is it, this is it. Just blindly put ij minus. So it's important we understand this right here. Okay? All right. We still have the diffusive flux for x momentum and diffusive flux for y momentum. Okay? So for the x momentum, not the x-dir diffusive flux. It should be called x momentum convective flux. It's the integral, surface integral of grad u, which is the diffusive flux, so minus grad u, right? Minus div minus grad u. So grad u dot n ds integrated over a u control volume. Okay, so grad u, remember, is du by dxi plus du by dyj, right? So dotted with n, that gives you du by dx here, du by dx, and du by dy, right? It's grad u, gradient of a scalar, du by dxi plus du by dyj, dotted with n. The unit normal here is 1, 0, 0, 1, 0, minus 1, 0, 0, minus 1, and 0, 1. So you dot them, you get these quantities over here. And we did this when we did the diffusive flux with the finite, when we began the finite volume method. Okay? So that would give you du by dx east times delta y minus du by dx west times delta y plus du by dy north times delta x minus du by dy south times delta x, right? Okay. Next, we need to approximate these derivatives like we did last time. We expected this from the finite volume method. Okay? So now we can just use centered approximations. Okay? Now, however, the spacing is more compact. Okay, we don't have a 2 delta x spacing between the cells. We have only a delta x spacing. So for example, du by dx east, this guy, is ui plus 1 minus ui over delta x. Okay? So your spacing with respect to the derivative is delta x over 2. So you're doing, with the finite difference method, we would have done a centered approximation. ui plus 1 minus ui minus 1 over 2 delta x, right? Here with the finite volume, we're doing ui plus 1 minus ui over delta x. So it's a more compact approximation. Okay, it gives you still second order approximation. Okay. Same thing with west derivative. Can you give me the west one? Du by dx west. So that's the one on the left. Okay, yeah. If you don't say the other index, I assume it's equal. So you say ui minus 1 over delta x, right? Okay, what about du by dy north? Over delta y, correct? And then finally, du by dy south. Uj minus 1 over delta y. Yep, exactly. Now you take those and plug them up in this equation, and guess what? You get the standard diffusion, you know, ui plus 1 minus 2 ui plus uj minus ui minus 1, right? The standard Laplacian that we would have expected, right? Except it's done with an integral approximation, okay? Because you have two steps with the finite volume, we could have done a different approximation from here to here and a different one from here to here, okay? But we chose to do something similar that would have given us similar to the finite difference, okay? So now this div grad, this is a div grad calculation over here, right? Because the diffusion term is div divergence of the flux, which gives you that del squared u. So this, what I did here is I did div grad, and it was consistent with the Laplacian, with the correct Laplacian. I did div grad u over here. And on the finite volume sense, because we placed the velocities at the faces, it did give me the correct compact Laplacian. Okay, it didn't give me a wider Laplacian. If you were to do this on a finite difference grid, it would give you ui plus 2 minus 2 ui plus ui minus 2. Okay, so that staggering compacts everything. Same thing with the y momentum diffusive flux. You have this integral, and then it's the same thing. You get these fluxes across the surface of the control volume. In this case, you're diffusing v. So grad v is dv by dx I plus dv by dyj. And the unit normal is going to be either 1, 0, 0, 1, minus 1, 0, 0, minus 1. And then you dot it, you get the correct component, so you're able to get all of those guys over here. Ends up being dv by dx east, and then dv by dx west, and so on and so forth. East and west with respect to the y momentum control volume. Okay, so this turns into this expression, dv by dx east times the area, delta y, minus dv by dx west times this area. Remember that minus comes because the unit normal is minus 1, 0, so you get that negative sign. Same thing for north, dv by dy north minus dv by dy south. Okay, it kind of makes sense when you think about if you're evaluating a derivative, right? Yeah, it's the derivative of the derivative, right? That's what this is doing, really. So if you think about this term here, this is the divergence of the derivative. This is derivative of the derivative. So it's really div grad what we're doing here, okay? And then you do the same approximations. dv by dx east is vi plus 1 minus vi over delta x. And then dv by dx west is vi minus 1 over delta x. I find it very useful to just put your finger, say it's this minus that, and then put the indexing, okay? Because if I were to close my eyes and just tell you out of the blue I plus 1, you'll get lost, right? So just put your fingers on it. For those on YouTube, look at the staggered grid, look at the control volume. The gestures I'm doing here in person is pointing out to where the variables are located and taking their differences. Okay, literally do this. It's gonna bring it here, right? This derivative is gonna bring these two quantities here. Same thing for the north. It's gonna bring this v minus vij over here. Same thing for this derivative, dv by dy in the south. It's going to be vj minus vj minus 1 below it, and then it's going to bring it here, okay? It's going to put the flux over there. Now, when you combine all of the fluxes together, this result lives here at the cell center. Okay? This result is the net contribution of all the fluxes, and we're going to assign it in the cell center. Okay? All right. Are you ready for the grid, for the staggered grid? Okay, this is going to be our staggered grid. This is what we print day in and day out. We have large printouts of this, small printouts. We have them on our desks. We give them out on the street, you know, to people if they're doing finite volume while they're traveling, right? It's busy, okay, but it would have taken me a heck of a time to animate this, so I didn't animate it. Okay, I did it. We can study it now. First, consider the red line. That's your domain boundary. Okay, that is going to be your domain boundary. This red box could be same size, number of points in x and y, or unequal size. It doesn't matter as long as they are structured and uniform. Okay, so that's what's going to matter. We cannot stretch the grid along the way. Delta x is the same everywhere. Delta y could be different, but is the same everywhere. Okay, so you get these consistent control volumes. And here I only drew it for 4 control volumes. Okay, but notice here I go P11, P21, P31, and then I go all the way to Pnx. Okay, now the reason I did this is because I like to count on the interior points, which is what is going to matter to us. Everything inside that, those red lines or in the gray area, is where we're going to do our for loops to compute quantities. And I made also one further assumption, and that is we will need ghost cells to have versatility when we implement boundary conditions. So if I were to start with the simplest quantity, which is a scalar, in our case, that's going to be the pressure. Okay, that's the only scalar we're dealing with right now. If you're doing an energy equation, for example, with temperature, you put the temperature with the pressure in the cell center. Okay? But my primary quantity for mass conservation would be the pressure. So I'm going to place it at the cell centers. I'm going to add a ghost cell on each side of the domain. So if I have nx grid points or nx cells, not grid points, nx control volumes and ny control volumes in the y direction, nx in x, ny in y, then with the ghost cell on each side, I would have nx plus 2 control volumes in total in the x direction and ny plus 2 control volumes in the y direction. And those would be these guys on the periphery of the red box. Okay? They're ghost cells. They're placed there for convenience. In fact, for the most part, we're going to just set them to 0 and never use them. But occasionally, for a certain boundary condition, we might need to put a value in the ghost cell just to make post-processing easy or some calculation easy. We'll leave it there for memory. Okay? And it will make all of our array analysis consistent. Because I know when I stagger to the left, so if you look at this P, I'm going to have a boundary point over here, okay? But no, if I stagger to the left, but no point over here for the u velocity. So crap, I need to, because I want to have the same size arrays for u, v, and p, so everything seems consistent and easy. I don't have to worry that, oh, the u velocity is n plus 3 or n plus 1 size, whatever. I want to have them all of equal size. So I decide to add ghost cells on the pressure, but also we will stagger the same way to the left, only to the left. So this ghost cell would stagger the u velocity to the left, so we'd have a u velocity over here. We're probably never going to use this. Maybe. But also on this control volume, we're going to stagger to the left. We will have a velocity here. This will be 0 if it's a wall. It will be some value if it's an inlet. Who cares? It's a variable. But I'm not going to place a velocity over here. Why? Because I want my number of points to be consistent across all arrays. So if you count P, you have 1, 2, 3, 4, 5, 6 P's. And you have 1, 2, 3, 4, 5, 6 U's. So they're consistent. In the X, same thing in the Y. 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6 P's. And then for the U's, 1, 2, 3, 4, 5, 6 U velocities. Okay? So indeed, my array for the U velocity is going to be the same size as P, and X plus 2 and Y plus 2. But in my mind, this is how they're located, because we chose to stagger them in that direction. Once you make that choice and you start doing your calculations, then your variables will be updated accordingly, and you'll get the correct flow. If you were to stagger things to the right, this would be flipped over. You would have everything going to the right and plus side. Same thing for the v velocity. We're staggering again to the minus side. So I'm going to stagger that entire grid. I stagger the p grid, OK? So I'm going to stagger it to the left. So the v velocities live here accordingly. And you have the same number of points. You can count them the same way I counted the u velocity. So when you spend a minute and think about this grid, you're like, yeah, you know what? It's not that bad. My reference point is going to be always the p pressure. But then I have to think, when I'm implementing the u velocity component for the u momentum, then I have to think that, yeah, this is my control volume. Maybe I'll grab one of the printouts and I draw a control volume with a Sharpie and start going down. I'm done with it, I throw it away and grab another paper and I draw a v control volume. You will see in some circles that they show you all three grids with squares everywhere. It's unreadable. Okay, I only show the square or the control volumes of the cell centers, okay, and then let you draw whatever component you need for whatever control volume you're dealing with. If you're doing only x momentum for now, you just draw a control volume around one of the velocities and start reasoning about, oh, I need a flux here, I need a flux there, oh, it lives where this is, what is the indexing here, etc. And you reason about it that way. Okay? So I'll give you this slide, and you can print it and think about it. It will be a great guide for us as we implement our finite volume driven cavity code and for your second project. Okay? This is the discretization piece of it. We have all the components for it. The time integration scheme is simple forward Euler, n plus 1 minus n over delta t, right? So that term is easily added to the equations. But we have the ingredients, all of the ingredients necessary. We're still missing a solution algorithm. Right? Remember last time I spoke about the difference between the numerical method and an algorithm. The algorithm here, the purpose of the algorithm is to figure out how can we get a pressure where there's no equation for the pressure, which is the projection algorithm that we discussed last time. Well, guess what? It's no different than last time. It remains to be the same. We can write these equations first. Assume we do advection diffusion only without pressure, and we will call this u tilde. Now you will notice that I will use this u tilde more in the finite volume discretization, because I need that temporary variable to store things in it. So I will use this nomenclature moving on. U tilde, an intermediate velocity field that's not mass conserving and that doesn't have a pressure. So as if you just take advection and diffusion out of only from the momentum equations, and then you correct that pressure field with you correct that velocity field u tilde with the velocity that you want to be divergence free, and you adjust it with a pressure gradient, like we discussed in the finite difference method, and which would give us the equation for the Poisson equation for the pressure. Del squared P is div u tilde over delta T. Okay, just like we did last time. Okay, it doesn't change. All right, doesn't change at all. Okay. Boundary conditions. Now we will have, once we get programming, we will have to talk about this. Once we get to boundary conditions as well, we'll have to talk about how we're going to deal with this equation. Okay, and so there'll be a time where we'll talk about this. Next will be boundary conditions, because I'm focused now on the lid-driven cavity. All I care about now are generally wall or moving wall boundary conditions. I will give you a hint on what to do with inlet boundary conditions, but that will be part of the derivation for your project. You'd need to derive the conditions for inlet boundary conditions. And really what it boils down to, in the end, we want to put boundary conditions on the transported variables, which are the velocities. Even if you say, I have a pressure boundary condition, well, yeah, there's no such thing as a pressure boundary condition. In the end, that implies something on the velocity. You have to figure out how to connect that with the velocity boundary condition. And we need to tie this in with what that implies on the pressure equation as well. All right, so we will start with walls, velocity boundary condition on walls. So these walls, they could be moving or they could be stationary, okay? So I will start with an example. You will notice that whatever problem I give you, you have to sit down and try to reason your way around the boundary conditions I'm giving you. Okay, so x minus, x plus, y minus, y plus. You have a moving wall, etc. I'll try to generalize as much as I can, but you will need to sit down and repeat the process. So I'm explaining to you a process. I'm teaching you how to fish, right? So that you can know how to fish yourselves, you know, later on with new boundary conditions that are presented to you. Okay, so wall boundary conditions, I'm going to pick the left side. So this red line here is my boundary. And the first interior cell is a P cell, right? So we take this boundary, and the first interior cell is naturally a P cell. And remember our indexing, we started from 0 all the way to nx plus 1. The 0 was in the ghost cell. The first interior cell was 1, and the last interior cell was nx and ny. Right? So we know on the interior we go always from 1 to nx and 1 to ny. 0 is in the outside, and nx plus 1 and ny plus 1 are in the outside on the other side. Okay? So, and then we would have this fictitious ghost cell, P0J I call it. And because we're staggering to the left, we would have the same index for those velocities as this guy. In the end, what you will do, you will take that diagram that I showed you and you say, okay, what is the boundary condition here? All the velocities on that line are going to look like this. Here's the formula. Slice them or do a loop over them in Python and you're done. Okay, that's the reasoning. But there are two things that you need to figure out when you are given a boundary condition is what do you set for the velocity and how does that affect the pressure equation? Because the pressure Poisson equation is tied in to this mass conservation. If you change the velocity, you're changing your mass conservation at the boundary. If you're setting the velocity, you're setting something in that div u. You're specifying one of the unknowns, right, there. And so you have to figure out what that implies on the pressure. That's what we will do in these slides. Okay? So same thing here. We're staggering to the left. This is my arrangement, you know, indexing whatever the indexing is. This is staggered to the left. So this would be same index as this. So V1J, P1J, V1J, U1J, and then V0J, V0J, P0J here. And then this would be J plus 1. This would be J plus 1. This would be I plus 1, which would be 2. Okay? Now, in general, at a wall, the normal component of velocity, in this case, for an x minus, so let's do it for a specific case, and then we will generalize. The x minus phase, u is 0, because it's a wall. There's no flow coming in. Okay? If it's an inlet, u would not be 0. It would be a different condition. Okay? So u is 0. But then v, now what's nice about u is that you can directly apply it at the boundary. Similar to the finite difference method, right? Because we have a degree of freedom at the boundary. So you would say for all of those velocities here, u1 for all j is equal to 0, right? At the x minus boundary, bam, you're done. Okay? You said that. Now for the v velocity, this could be a sliding wall, like a driven cavity, right? So the v velocity could have a non-zero, you know, value. Okay? It doesn't mean that the flow is coming in. It just means the wall is sliding. The wall is moving. Okay? But we don't have a degree for freedom for v. Okay? So we don't have a value of v here. We don't have a variable for v here at this point or at this point, right? All we have is a degree of freedom outside in the ghost cell and this one on the inside. So what do? We use that same approximation we did with when we talk about finite volume first time, is we use the ghost cell to set a value that uses the interior value to produce on average the desired velocity at the wall. Okay? That's what you lose when you go to staggering or finite volume, really. You lose that degree of freedom at the boundary that you had with the finite difference method. Finite difference method, we had the point at the boundary. We specified the value directly over there. Here, you can't do that. The best you could do is set. Now, why do I set a value in the ghost cell? Because if I set it using the interior value from the previous time step, on the new time step, I come to this control volume, V1J, and I'm calculating fluxes The flux coming from the left side, oh, I already have some value over there, and I'll just use that. Does that make sense? That's it. That's the benefit of that. Okay? Rather than saying, well, you know, on the left side, the left flux or the left value is given to me. I'm going to bring that into the flux. You don't worry about that. You just set values in the ghost cells so that your for loop on the interior doesn't worry about boundaries. It just goes everywhere, and there's values where it needs to, right? So when you come to this control volume, there's going to be fluxes coming in and leaving, right? Well, guess what? You have a value over here already set. That's the benefit of using this ghost cell. It's entirely programmatic in nature, okay? All right, so then mathematically, this would look like that. V interior plus V ghost over 2 is equal to V wall. The average between these two velocities is equal to V wall. Same thing for these two guys, okay? Now, what that means, as you run your code, you will notice that the values in the ghost cells are going to change over time because the values in the interior are changing. So the ghost cell is going to change as well to produce V wall on average, right? So it's always changing over time. In a way, it's like almost a time-dependent boundary condition, okay? So then what you would say, V1, U1j for all j is equal to 0. And V1j plus V0j over 2 for all j is equal to V wall. So you could slice this in Python. Say take all of these guys. So you would set V0j equal to 2V wall minus V1j, okay, automatically in the code, right? So you set your ghost cell. All right, so now let's take the y plus and repeat the same procedure. So I'm trying to explain to you the process so that you can reason about it on your own. Yeah.
Most of the time we're giving you all, right?
You will be, yeah, if it's a sliding, if it's a stationary wall, it will be U and V equals 0. If it's a moving wall, I will give you the tangential component, right? If it's an inlet, then the normal component would be non-zero.
So but then you calculate the ghost cell, right?
On the component where you don't have a degree of freedom for, right? So, yeah, so if V wall is 0, okay, so I think that's your question. If V wall is 0, then V ghost would be equal to minus V1, minus V interior, right?
Yeah, so, but we wouldn't type it into Python like that.
Yeah, in Python, you would set the ghost cell values using the interior value. So you begin the time step, okay, with your previous values. You say, okay, what are my values in the ghost cells?
You want your ghost based on your interior and your wall.
You would set your ghost cell values based on your interior values, and then you do the time advance. Then, I don't understand the question, I guess.
Yeah. I think maybe just
We will set the value in the ghost cell. At the beginning of the time step, we're going to take whatever exists on the interior. We set a value in the ghost cell, and then we do our loop. Because I don't want to stop my loop at the boundary. I'm going to loop over all the interior points, and I'm going to need a value I'm going to step outside the limits of the interior. And I need a value here, and that value has already been set. Okay, that's the advantage of that. So I would set it at the beginning. But yes, there is memory location for that ghost cell value. Okay? Once we program it, it's probably become clear. Okay, so now if you do the same at the top wall, at the y plus, so that would be like the driven cavity problem. Okay? So in this case, V is 0. There's no velocity entering the top wall, but the top wall is moving at a U wall. So in this case, I do have a degree of freedom on the wall for the V velocity, right? So I can set that directly to 0 on all of them. But for the U velocity, which is sliding like this, I don't have a degree of freedom, so I have to take the average. So I take the average of those two equal to U wall. I would put the value in the ghost cell using the interior cell. So it would be the same formula, okay? But you have to reason about that at each side, okay? At each side. Do you have a question? So in other words, if you were to go to this grid, you would say, okay, I have a wall over here, U and V are 0. I can directly set these values to 0 because they're all U. But I don't have a variable V over here. I only have v here and v here. This is being part of the solution process. I'm going to use the old values to set a value here that on average produces a 0 v. Okay? So I set a value here, and then I run my time advance. When I hit this control volume, this v control volume, I'm going to use fluxes between, doing averages and whatever. Well, guess what? I have a value already here that will produce a net zero velocity here, which is good. Okay? Top wall, you say, well, okay, my v is 0 everywhere, so I can set these points to 0. But my u, I'm talking about the top wall, it's a sliding wall. I don't have a u variable living on this wall. So I have to set the ghost cells. Okay, so I use the average of these to reproduce u wall. Okay, that's the reasoning I'm trying to convey to you. Okay. All right. So in general, for walls, the normal velocity component is 0 because it's impermeable walls, right? There's no velocity flow coming in. If it was permeable, it would be an inlet, okay? Be a velocity inlet, different question, okay? And the tangential component of velocity at the wall can be non-zero or could be 0 if the wall is sliding, for example. So top-driven cavity, or if you want to move the wall on the left, it would be sliding up or sliding down and so on. Okay? And then the way you do it, I like to use this nomenclature, U interior and U ghost, right? So think of it this way, and then go figure out what the indexing need to be based on that grid that I will print for you. Okay? That will give you. Okay, so now good, easy for the velocity. What about the pressure equation? What are we going to do for the pressure? Now, the pressure equation, we had that del squared P equal U tilde over delta T. So what are we going to do for the pressure as we approach the boundary? If you're specifying the velocity, you know something about the flow. So the pressure cannot be arbitrary over there. Last time we reasoned, we said if you know the velocity, that means you don't need a correction on the pressure at the boundary, right? Because you know the velocity, you know the truth, so U and U tilde are the same. There's no pressure gradient. So in a way, it implies a 0 pressure gradient. So today, I'm going to show you a different derivation that is a stronger statement than what I just said. Okay? And it has to do, essentially, with mass conservation. So for the pressure equation, all I care about are the cells at the boundary for the pressure equation where I have a velocity specified. And the ghost cells, I don't care about mass conservation in the ghost cell. They can go to hell, the ghost cells, okay? I don't care about that. Whatever value is in them. What I care about is to conserve mass in the interior cell. So take this x minus site, for example. What I'm going to do to derive a condition on the pressure is I'm going to apply the continuity equation, the continuity, not the pressure equation, the continuity equation, here in this cell. Okay? So it would be U2 minus U1 plus Vj plus 1 minus Vj, okay, over delta y, etc., equal to 0. So let's see how that works. So if I apply the continuity equation to this control volume, this is the first interior control volume. That's what matters to me. Why did I do it here? Because I have a boundary condition here. I want to see what happens when I specify this or when I set this equal to 0. I want to see what happens to the pressure. So here's one way to derive it. So you take that continuity equation, and then you recognize that u n plus 1 for all j, u1, this u over here is 0 because it's a wall. It's impermeable wall. There's no flow coming in, so it's always 0. Okay? So I can set this guy to 0 over here. This guy would disappear. Okay? So I'm doing the math for the continuity equation. So this would imply that, okay, at least we got rid of this term here. We have now, for continuity in this control volume, it's U2j at n plus 1 balanced by those other two. We need to conserve mass on these three velocities. Now remember our projection algorithm. It says that un plus 1 is u tilde minus delta t dp by dx, or dp by dy. So it's n plus 1 is u tilde minus delta t grad p. So I'm going to substitute this one with u tilde and delta t dp dx, and this one v tilde dp dy and v tilde dp dy. Because I'm trying to infer something on the pressure. Okay? Almost done. I know we're running out of time. So when you make this substitution, which is a true substitution, we assumed this from the beginning, okay, and you rearrange terms, you get this equation. Something on the pressure. This reminds you of the second derivative of p in the y direction, right? This looks like d2p by dy squared. But this almost looks like d2p by dx squared, but it's missing some terms, right? And on the right-hand side, you have something that looks like dv by dy. And if we had a u1 over here, this would be du by dx, right? Well, in fact, this equation, if you compare it to our Poisson equation, it's the same as the Poisson equation for the pressure, except that at the boundary, we eliminated some terms on the pressure. How did we eliminate them? Essentially enforcing dp by dx equals 0 on the pressure at the wall boundary, because we know the velocity. But this is a stronger statement of that derivation, right? Because we started with the continuity, we eliminated the 0 velocity, we did this assumption and derived all of this. So in practice, what we do, we solve this equation everywhere, except at the boundaries, all we do is we adjust the coefficients. Remember when Maher presented the Poisson equation with east and north and south and west coefficients? That's what we will do. What will happen is that when we get close to the boundary, there is no more coefficient for the pressure term. There's no more connection to P0J, okay? It's gone. So we will set the coefficients accordingly at the boundary. So we will do this very intelligently. We will build essentially like the full matrix for the pressure equation and set the coefficients to 0 where we don't need them, okay? So this is identical to this, except we eliminated some terms based on what we know about the velocity, okay? Again, you have to derive this every time, okay? Every time. That's what YCFD is hard. You have to think about this all the time. But once you do it a few times, you know, it becomes, you start building a repertoire of knowledge of what you need to do, okay? Again, and we're just scratching the surface. We didn't talk about inlets or outlets or other complex boundary conditions. Okay, so I'll let you go. On Thursday, bring a cup of coffee or tea, some food or something. We're going to get programming. We're going to program this, even if it takes us 2 hours. We're not going to leave until we get this the entire algorithm put in a code. And it's going to be hard. There's going to be a lot of indexing. And the pressure is going to take some more time for us to reason about. Okay, but we will show that we'll get discrete mass-conserving flow fields on the lid-driven cavity problem. Okay? And in your project, in your second project, you will have to think about what happens to this equation when you have an inlet velocity. So I'm going to do like a jet flow over an object, okay, with an outlet. So you have to think about what happens there. All right? Thank you.